Hi guys, Kenna here. So this is part two of ray tracing diagrams. In part one, we went over how to do this for concave and convex mirrors. Here we're going to go ahead and look at doing it for lenses. Again, concave and convex. We'll go ahead and take a look at converging lenses or convex lenses first, then take a look at concave or diverging lenses as we go ahead and finish up. The key concepts in terms of the basic terminology are very similar to what we talked about with with mirrors. And so if you remember those, a lot of this should sound pretty familiar. We have the center of curvature. Now, the one thing that's a little different here is in most of your diagrams, you're going to see 2F instead of C, the C for the center of curvature, but it's essentially the same thing. Instead of dealing with a spherical mirror, however, we're going to be dealing with the curvature for the lens. And so we can go ahead and cross this out here and replace it with lens. So mirror gets replaced with lens, mirror gets replaced with lens, and mirror gets replaced with lens. Okay. When we go ahead and start looking at this, the pole is still kind of the same place. They don't always use the term pole, but essentially this is the center point where the spherical lens lines up to the principal axis. You have the radius of the curvature, the distance between the center of curvature and the pole. You still have that in terms of how the lens is set up. We don't usually use that term as much because they're focused more on the lens, but it still exists. And then definitely still used is the focal point F. And if you notice, the center of curvature 2F is simply twice the distance F is. And you get the focal distance of the lens by looking at the distance from the focal point to the actual center line of the lens itself. And the principal axis is essentially the straight line that's perpendicular to the center line of the lens by which we're kind of viewing the whole setup. Okay. And so that's kind of what we're taking a look at. And again, there's a lot that's in common when we go ahead and look at this versus the mirrors that we did in part one. The rules are similar, but not exactly the same. Okay, so for convex lenses, which we're going to start at, remember that these convex ones are the converging lenses. Rule number one, a ray of light which is originally parallel to the principal axis passes through the focus after refracting through the lens. So it comes in parallel, hits that midline of the lens, and then refracts down through the focal point. Okay. Rule number two, the second ray is a ray of light passing through the optical center of the convex lens, and it doesn't bend. Okay, so it goes straight through the lens because it's kind of hitting it at a point that doesn't bend. And so when you do this, this is the point where the principal axis meets the center line of the lens. That's the point you're going to go through, and it doesn't deviate. And then the third rule is when a ray of light passes through the focus on the convex lens, then it becomes parallel coming out the other side after refracting through the lens. So let's go ahead and take a look at what this looks like. So again, I'm just going to go ahead and use an arrow for my object. That's going to make it easier for us to kind of follow these points. Notice that the eye is on the other side. It's not bouncing back like in a mirror, but it's actually going through the lens this time. We need to label a couple of points, same points we kind of did last time. You have your 2F, which was C last time. You have your F, which is your focal point. Remember, the distance from the focal point to that center line is what is known as the focal length. And then 2F is what would be the center of curvature. But because this is what's known as a double convex lens, we're actually going to have this on both sides. And we need to have both of those measurements there. And they'll typically give you either F or 2F. And if you ever buy lenses, they typically give you the focal length. So if you want to create a diagram, you can measure out the focal length and then double it to go ahead and get the 2F point. All right, so we'll go ahead and do our first ray. First ray is going to come off the top of our object, going in parallel. As it comes into that center line, it will refract and go through the focal point on the opposite side. Now, I'm going to go ahead and go to rule 3 from the previous slide because I just still think it's easier if you do these two rays first. In this case, we're going to go through the focal point on the near side until it hits that center line for the lens, and then it's going to come off parallel. So we can draw it here, and that point should be the point at which we go ahead and find our object. But again, we like to have at least 3 rays just to double check ourselves. The next one's going to go through essentially the pole, the midpoint of the center line of the lens where it meets the principal axis. And so we draw this one through, and we'll notice that they go ahead and overlap each other at one particular point. The more accurately you draw your lines, the more likely it is for them to actually converge. Then we go ahead and put our object here. Now, when we go ahead and do this, we still want to go ahead and identify the location, the size, the orientation, and the type. So we're going to go ahead and write those down because this is the same thing we did last time, and we want to make sure that we include it here as well. So let's go ahead and start with the location. Okay, location is going to be opposite side over here, and it's going to be between F and 2F on opposite side of lens. Okay, so we got location. Let's take a look at size. So size is the next one. Well, pretty obvious to see that this is reduced. Okay, reduced as opposed to magnified. We could have same size. That's what would happen if we put it on 2F. But for here, we're going to go ahead and say that it's reduced. Then we're going to go ahead and take a look at orientation. And what we're looking at here is if this is upright or inverted. And obviously, as we take a look at that, that's going to be inverted. And then the last one we want to take a look at is type. Now, when we say type, what we mean is real or a virtual image. Now, if we take a look at this one, they're solid lines. So these are real lines that are converging together. So this is going to be a real image. Okay, so location between F and 2F on opposite sides of the lens, reduced, inverted, and real. And those are the basic things, and that should sound somewhat familiar because we've seen something very similar to this when we went ahead and did the concave mirror. So let's go ahead and compare those two as we go ahead and move on. Thank you to Step by Step Science for this. Remember that 2F is basically the same thing as C. We just don't typically use the C for center of curvature when we're looking at lenses. If you go ahead and take a look here, if we look at convex lenses, if the distance is greater than 2F, the image location is between 2F and F. And if you look at concave mirror, if it's greater than C, the image location is between C and F. And so very similar at 2F, at C, greater than 2F, greater than C, no image, behind lens, behind mirror. So this table is a great way to kind of compare the two. They are very, very similar. Now, the one thing I might change, the terminology that we've used versus what's on this table, is when we get to orientation, we don't really talk about erect. The term we typically use is upright, and so you can take a look, if you're filling out this table, you can go ahead and use the term upright instead of erect. But you can see that as you go ahead and begin to think about where your placement is, as you go ahead and move the object in closer towards the lens, okay, it begins to get larger and larger, and once you cross the focal point, we actually switch to an upright image, super magnified, but it's virtual because we have to go ahead and do some back tracing. Okay, same thing is true for concave mirror and convex lens. All right, so we've done the convex lens or the converging lens. Now let's go ahead and take a look at the concave lens or diverging lens. Again, 3 rules, again, slightly different. Rule number 1, a ray of light parallel to the principal axis of the concave lens appears to be coming from focus after refracting through the lens. Okay, number 2, a ray of light passing through the optical center of the concave lens goes straight after refracting through the lens. And then rule number 3, a ray of light going towards the focus on the other side of the concave lens, so this one's a little different, becomes parallel to the principal axis after refracting through the lens. So let's go ahead and take a look at how that plays out. Again, we're going to go ahead and use an arrow to represent our object. Just makes things pretty easy. We have to label our spots. There's 2F and F. Typically, again, remember you use the focal point. That's what comes with most lenses. And then you can double it to go ahead and get 2F to do your ray diagrams. On the other side, we're dealing with two curves, two arcs. So we also have F and 2F for this one as well. And the eyeball is on the other side because it's a lens and the light is intended to go through. All right, so our first ray is going to come in parallel till it hits that center line on the lens, and then it's going to refract, but remember this is a diverging lens, so it's actually going to go away from the principal axis. We see something like this. So if you remember, when we did our convex mirrors, we had to do a special thing called back tracing. We're going to go ahead and do the same thing here, as to where our eyes are going to feel like the image comes from. So let's do a little bit of back tracing. All right. Notice that when we do this, you can see that when we're drawing our ray that's going away from the principal axis, it's as if it was coming from the focal point on the near side. Okay. So again, the ray that's refracting out from that center line of the lens looks as if it's coming from the focal point on the near side. Okay, the next one that I'm going to do, again, I'll kind of go ahead and skip step 2 and do step 3. We're going to go ahead and have it coming in as if it's going through the focal point on the other side and then coming off parallel. And we'll backtrace this one as well. Okay, we'll backtrace this one as well, and you'll notice that we have a nice point where there's convergence between the two backtraced rays. Now I'm going to go ahead and throw that third one in, and the third one is going to go through that optical center, the pole, the point at which the center line of the lens meets up with the principal axis. And you'll see they actually converge really well in this particular example. In your drawings, again, they may be off a little bit, but you should get a pretty good idea. So we can go ahead and draw our image in right here. Now, again, just like last time, I want to go ahead and finish by going ahead and including location, size, orientation, and type. Let's see, maybe this time I will go ahead and put them in the bottom right here. So let's go ahead and start out with location. So the location of the image, you'll notice, is between the focal point on the near side and the lens. When we go ahead and take a look at the size, this is going to be diminished. When we go ahead and look at the orientation, this one's going to be upright. And then we finish with type. And as you can see that these are those dotted lines, these are not real light rays, unlike the previous example. So for this particular example, we're going to use virtual. All right, so what are the basic rules or patterns that you hopefully will go ahead and take out of this? When you're dealing with converging or convex lenses, if the object is greater than 2F, you will see an image between F and 2F that is inverted, diminished, and real. If we put the object right at 2F, the image will be at 2F. It will be inverted, but it'll be the same size, and it will also be real. If you move the object to between 2F and F, the image will be greater than 2F distance from the lens. It'll be inverted, magnified, and real. Okay, at F, we shouldn't have an image, it's switching. And then at less than F, it'll be behind the lens, upright, magnified, and virtual, because again, we have to do some back tracing. When it comes to concave or diverging lenses, concave lenses are always going to be between F and the lens. They're going to be upright, diminished, and virtual, but they will increase in size as you go ahead and approach the lens. Okay? All right, so Hope you have a basic understanding of how to do these ray tracing diagrams with lenses, and it's very similar to what we did when we were going ahead and looking at mirrors. So again, if you're still not quite following this, please go back and rewatch the mirror video first and then come back and rewatch this one and keep track of the lines. This is why I went ahead and used the different colors. So hopefully you can go ahead and track through with the different colors for the lens rays. Okay. All right, guys, that's all I got for you today. Stay healthy, stay safe, and I'll hopefully see you soon. Take care of yourselves. Bye-bye.